Since coming to BYU in 2002, Professor Guthrie has been a private consultant to industry and government on a variety of road safety issues, such as the susceptibility to frost damage of subsurface soils and the impact on roadbeds of excessive heavy transport vehicle axle weight, among several others. He is the recipient of a number of research grants and is the principal co-investigator on a recent $150,000 grant from the Alaska University Transportation Center to study the effects of warm weather thawing on roadbeds. Professor Guthrie is the author of over a dozen referee journals and of over 50 conference presentations. In the last 3 years, Professor Guthrie has also found the time to be faculty mentor to 5 different engineering student researchers who have received ORCA grants here at BYU. It is with a great deal of pleasure that we welcome today our featured House of Learning lecture speaker, Professor Spencer Guthrie.
Thank you, Mr. Champion, for the introduction, and thank you, ladies and gentlemen, for your participation in this House of Learning lecture. As Mr. Champion indicated, the topic of my presentation is Crumbling Concrete, Salt and Safety on Utah Bridges. This topic has received increasing attention in the media recently with the collapse of the Minneapolis Bridge and also approximately 1 year ago, the collapse of the Laval, Quebec Bridge in Canada. This leaves many in the public asking the questions, what is the state of our infrastructure and what is being done to keep these disasters from occurring? I'll address both of these questions in my presentation. During my 5 years at BYU, my research assistants and I have been investigating, in particular, the quality of bridge decks in the state of Utah. We've tested almost 30 bridge decks, primarily centered in the I-215 and I-15 corridors. We've also conducted national questionnaire surveys on this topic, and we've led scanning tours to other state departments of transportation to learn more about the bridge management practices in other locations. Here we're conducting a test on a bridge in New York. The gentleman standing with me is Daniel Shao, also a BYU graduate, who is a senior project manager with the Utah Department of Transportation and also the director of the project, which I will share with you at the end of this presentation. Here's a picture of a typical bridge deck. The deck itself is about 8 inches in thickness, and it contains 2 mats, or layers of reinforcing steel, or rebar. Each mat is about 2.5 inches from the top and bottom of the bridge deck. Over time, bridge decks deteriorate. They deteriorate due to traffic factors, environmental effects, material property deficiencies, and other factors. Here's a picture of a typical distress, in fact, the most common type of distress that we see in bridge decks. This is a transverse crack adjacent to the hammer shown in the picture. This crack, like many types of distresses, can be seen with the naked eye. It can be measured and quantified and reported as part of a visual distress survey. Other types of distress common on bridge decks are shown in this slide, which is the result of a 2003 questionnaire that my previous student, John Hema, performed of 28 state departments of transportation across the northern tier of the United States. We see that, as I mentioned earlier, transverse cracking is most common, followed though by delamination. Delamination is a type of distress not visible from the pavement surface. This is a subsurface detachment of the concrete just above the top reinforcing steel from the underlying concrete substrate below the reinforcing steel. Delamination, while it cannot be seen visually, can be detected using acoustical sounding, including chaining. I'd like to show you a brief video clip that documents 3 different ways by which we can see delaminations. I'd like you in the video to pay particular attention to the areas which are hollow or sound dull. Those correspond with the delaminations. Okay, another time. Ooh, that wasn't bad. Come back. One more time. Okay, again. That's pretty good. Yeah, real firm. Okay, come back. All right, could you hear the hollow sound as the chain especially was dragged across the surface of the concrete deck? Over time, those delaminations will manifest themselves at the surface through the occurrence of potholes, as shown on this bridge deck surface. As we zoom in, we can see clearly the top layer of reinforcing steel, or rebar, present in the bottom of the potholes. Over time, as the deterioration continues, these grow. This slide shows a typical repair becomes a multitude of problems for maintenance personnel who are charged with maintaining the surface of the bridge decks. This effect, this growing effect, is called the halo effect, and I'll speak more about it later in the presentation. As you can surmise, with increasing deterioration and increasing patchwork, the structural integrity of the deck is compromised. I'd like to share with you some condition data for Utah bridges in particular. In 2004, 8.6% of the nearly 3,000 bridges in Utah were structurally deficient. Another 8.5% were functionally obsolete. And nearly 90% of Utah bridges needed some form of maintenance. The cost of the repairs was estimated at more than $1.4 billion. Now, I suspect that some of you are interested to know the exact locations of these structurally deficient bridges. They are represented in this slide as the green dots across the state of Utah. Those are structurally deficient. State departments of transportation across the nation, like Utah, are facing this problem. What, you might ask, is the root cause of the deterioration of concrete bridge decks in the northern tier, such as in the state of Utah? We asked this question in our questionnaire survey conducted in 2003, and we learned that salt-induced corrosion of reinforcing steel is the #1 leading cause of bridge deck corrosion. Answers in the other category were varied, but predominantly addressed construction aspects. Let's talk a little about salt and corrosion. Safety is the #1 parameter in all engineering aspects, and when drivers apply the brakes, they need to be able to stop. Because bridges are elevated structures, they cool from both the top and the bottom of the slab. Therefore, they can freeze rapidly compared to a pavement structure which is situated on the ground. Consequently, bridges have huge potential for severe icing problems. To combat the otherwise slippery condition, departments of transportation routinely apply de-icing salts on our highway bridges and roadways to reduce the effect of icing. Here's a picture of the salt that's accumulated on a bridge in New York. And to give you some idea about our application rates in Utah, we apply about 250 pounds of salt per lane mile with each de-icing event. So to put this in perspective, to treat the entire length of University Avenue here in Provo and Orem, we would need 15,000 pounds of de-icing salt with each event. Now, surely you must be asking, where does all of this salt end up? Well, some of it is splashed up onto our vehicles and carried other places. Some of it is caught in drains and outlet boxes on the bridges. Some of it, unfortunately, goes through leaky joints like this one, and the salt ends up corroding the substructure of the bridge. This is a local facility, by the way. And ultimately, some of it ends up in the concrete itself through a process called diffusion. We're looking at the side profile of a bridge deck, the upper 2 or 3 inches. This is the top mat of reinforcing steel, or rebar. Concrete itself is composed of gravel, sand, and cementitious products. The cementitious products are the result of the hydration of cement, a white powder which is added to concrete to cement the sand and the gravel together. Concrete has an internal void structure, which in most cases is at least 90% saturated. The concrete pore water provides a pathway for the chloride ions to enter the deck. As the ions approach the rebar, they can then cause corrosion of the reinforcing steel. Now, when the sodium chloride dissociates or dissolves in water, it produces a sodium ion and a chloride ion. The chloride ion is the one of greatest interest. I've shown you here the types of de-icing salts that are most commonly used. You see sodium chloride is by far the most common, and we have a huge abundance of this right near the Great Salt Lake in Utah. Other types of de-icing salts include potassium, magnesium, and calcium chlorides, all chloride-bearing. In some cases, calcium magnesium acetate is used. It's used especially in environmentally sensitive areas, but it is quite expensive. So we continue to use sodium chloride. This schematic, courtesy of the Sika Corporation, gives us a picture of the 4 components of the corrosion circuit, namely a cathode and anode and electrolytic path, which is provided by the pore water, and a metallic path, which is the steel itself. As chloride concentrations increase around the rebar compared to other locations, that location becomes the anode, and that's where the actual corrosion occurs. Because rust itself is 500 to 700% larger in volume than the parent material, it produces a bursting stress within the concrete. Concrete is not good in tension. In fact, its tensile strength is approximately 1/10 that of its compressive strength. And so cracking, initially horizontal cracking and then vertical cracking, occur quite readily, and then soon we have the birth of a pothole. Another consequence of rust is the reduction in the cross-sectional area of the steel, which ultimately leads to a reduction in the load-bearing capacity of the bridge deck. After a while, the maintenance forces will come along and finally replace this deteriorated concrete. They'll replace it with chloride-free concrete in this patch, and then subsequently, this part of the system, previously the cathode, will become the anode, now having greater chloride concentrations than its adjacent steel. And now the corrosion process will be initiated at this location. Thus, you see how the halo effect occurs in the field, a continuous growing of this damage process. Now, what can be done to stop this corrosion or to retard it? The first thing that DOTs have to consider that I'm going to share with you is increasing the cover depth. This typically ranges between 2 and 3 inches, although I've seen it as low as 1 on some bridges here in Utah. By increasing the thickness of the cover, even 1/2 inch, we can improve the service life of the deck up to an additional 6 years. So, for example, increasing the thickness from 2 inches to 3 inches for decks similar to those that we tested will provide a 12-year increase in service life. We've simply delayed the arrival of chlorides at the level of the reinforcing steel. However, after that 12 years has elapsed, now the chlorides are again arriving in critical concentrations at the level of the steel. What can be done then? To answer this question, let's talk about the type of reinforcement that's available. Again, these are results from the questionnaire survey of several state DOTs. You see that many DOTs use epoxy-coated rebar. This is commonly recognized by its green color. As long as the epoxy coating is intact, that is, no defects, no holes, no scrapes, the epoxy will prevent the chlorides from coming into direct contact with the steel and thus prevent corrosion altogether. However, for this to be successful, all parties involved with transportation, handling, and placement of this must be careful. And even with field cuts, such as is shown here, a epoxy compound patch must be applied to prevent localized corrosion at that location and ultimately shearing of the bar. Unfortunately, though, in too many cases, proper handling techniques are not utilized, and in fact, the ribs of the rebar are scraped. As the workers strike the tie wires down, they strike the epoxy coating of bars beneath, causing dings and other defects in the epoxy coating, and in many cases, the bar begins corroding even before the concrete is cast around it. In fact, in our field testing, we found that approximately half of the decks that we tested, which were known to have epoxy coatings, did not exhibit the properties of protection that we expected. In fact, they were as though no epoxy coating was present. This is unfortunate, but it emphasizes the importance of proper construction. The third and final type of protection I'd like to share with you is the use of surface treatments on bridge decks. You're looking in the center at the original concrete surface. What's been placed on it is an epoxy product, which is placed in a liquid form, and then afterwards, aggregates or small rocks are broadcast into the epoxy to produce a very highly skid-resistant surface that, when placed properly, will provide protection against chlorides and water. That is, it will be impermeable to the ingress of water or chlorides. In this case, no doubt the surface was not prepared properly, and debonding of that layer occurred. I'd like to show you a video now documenting the application of this kind of product on the roadway. The video was prepared by two of my students, Tyler Nelson and Reuben Collins.
Bridges typically have a design life of 50 years, but a bridge will only last that long if it receives proper maintenance. One way UDOT hopes to extend the life of Utah's bridges is by applying an epoxy to the surface. This film is intended to document this preventative maintenance performed on the ramp connecting northbound I-15 to State Road 201 in September of 2004. This ramp was built during the I-15 expansion project just prior to the 2002 Winter Olympics. For this project, Granite Construction is working with Polycarb Incorporated to apply 100,000 square feet of Flexogrid. Flexogrid is an epoxy-based polymer concrete designed to protect concrete from the damaging effects of traffic and especially de-icing salts. If salts are allowed to penetrate the bridge deck surface, they will cause corrosion of the reinforcing steel, which leads to bursting stresses and cracking as well as strength reduction. Before any overlay materials can be placed, the surface must be prepared. The tremendous strength of the epoxy is wasted if it is bonded to a layer of paint, deteriorated concrete, loose debris, or any other substance that should have been removed prior to application. Failing to properly clean the surface contributes to the occurrence of delamination and blistering, which lead quickly to cracking. Here's an example of an overlay that has failed, likely due to poor surface preparation prior to polymer application. This is exactly what UDOT hopes to avoid by properly preparing the deck surface. Shot blasting machines pummel the riding surface with steel pellets, which are then picked up and recycled using a powerful magnet. The effects of these machines can clearly be seen on the deck. The edges are inaccessible to the shot blasting machines, so handheld sandblasting hoses are used to clean these areas. Grinding machines are used to scrape the painted lines off the surface. Once all the blasting is complete, the deck will be cleaned with a vacuum truck to ensure no sandblasting grit or steel shot is left on the deck. Once the deck is cleaned, the drainage grates and expansion joints must be covered, or they will be filled with epoxy, potentially rendered unusable. The final stage of deck preparation entails the application of a low-viscosity methacrylate. This material is intended to penetrate and seal the small cracks that have formed in the concrete in the years since its construction. Once the cracks have been sealed, the deck is ready to receive the Flexogrid overlay. The Flexogrid is automatically mixed in the polycarb trailer and dispensed onto the deck surface at about 100 degrees Fahrenheit. Heating the epoxy greatly increases the speed at which it will cure. Once the Flexogrid binder hits the deck, it is immediately spread onto the deck surface using squeegees and showered with aggregates. When this layer of epoxy and aggregates has hardened, the loose material is removed and a second layer of binder and aggregates is applied. The two layers combined will have a thickness of around 5/8 of an inch. Eric Wells of Granite Construction explains some of the reasoning behind choosing to overlay the deck with FlexoGrid. Polymer concrete overlays can be installed and ready to receive traffic much faster than concrete overlays, and with much less additional dead load being added to the bridge. This fast turnaround reduces the amount of time the bridge must be closed and goes a long way to justify the increased cost of materials associated with polymer concrete. In this case, the cost was about $4.10 per square foot. To put this quick turnaround time in perspective, under favorable conditions, FlexoGrid will cure in 4 hours, while a standard 2-inch concrete overlay takes 7 days to fully cure. Polycarb is the only company that Mr. Wells is aware of that uses a trailer to automatically mix and dispense the chemicals and aggregates used in the overlay. The same process performed by another company could take considerable more time and manpower, or both, to apply because they involve using a trash can and drill to mix the polymer and bucket brigades to spread the material onto the deck. The heavy aggregates must then be carried out onto the bridge and dispersed by hand. Another benefit of using a trailer to carry materials is that reloading the trailer with aggregate is a fairly quick process. The aggregate is loaded into the trailer using a large forklift. Using the Polycarb wagon, 100,000 square feet of overlay can be applied to the deck, cure, and be open to traffic in less than 48 hours and can be expected to last in the neighborhood of 15 years with minimal maintenance. Mr. Wells also explained that in his experience, other overlay systems involving a waterproofing rubberized membranes under a layer of asphalt can be expected to fail after 2 to 3 years of use. Bruce Roeder, a chemical engineer for Polycarb, explained, in addition to most of the facts presented in this film, that this year alone Polycarb anticipates construction of 1 million square feet of overlay. This shot clearly contrasts a concrete pavement that has been overlaid with a concrete pavement that has not.
Okay, from the video you learned that these surface treatments can last up to 15 years. In research that was performed by my student Amy Birdsall, we found that these surface treatments should be applied between 1 and 15 years after construction of the new deck. Otherwise, sufficient quantities of chlorides have already entered the deck, corrosion has already commenced, and the expenses associated with the epoxy overlay are of no value. So, UDOT in particular has found great success in applying these within 1 year after new construction. By acting quickly, they dramatically reduce the exposure of these new decks to these aggressive chloride ions. Ultimately, though, unless the surface treatment is restored, replaced, or repaired, chloride ions will again begin entering the concrete. And when they do, ultimately the bridge deck will require some form of maintenance, rehabilitation, or replacement. These are costs associated with these activities here in the state of Utah. The cost for preventive surface treatments at $6 a square foot is only a fourth that of minor maintenance activities in the deck maintenance category. Notice again that those costs are a third to a fourth that associated with deck replacement. So an efficient bridge deck management program will focus on preventive maintenance. Finally, when repairs are required, inevitably the bridges are closed. Not only does the agency repairing the bridge incur specific costs, but the public also incurs real costs. The drivers who would otherwise frequent these corridors must now drive in a delayed fashion down detours, consuming more fuel, spending more time, putting more miles on their vehicles. These things add up to real costs. We call them user costs, and a progressive-minded DOT will consider the amount of user costs when selecting a particular strategy for maintenance, rehabilitation, or replacement of a bridge deck. I'd like to share with you a particular project where UDOT decided to pay a little bit more money up front to nearly completely eliminate the user costs associated with this project. This is 4500 South on I-215 East in Salt Lake City. This bridge will be removed and replaced this weekend. That's right, ladies and gentlemen. In 2 days, this bridge will be removed and a brand new bridge deck will be installed in its place using accelerated bridge construction technologies. Traditionally, Construction would require between 5 and 9 months. During that period of time, the bridge deck would be closed. The frontage roads that face the bridge would be affected. Traffic in the whole region would be adversely affected. You might ask, what is the user cost associated with this particular intersection? UDOT engineers computed it to be $33,500 per day, which is about $1 million per month. So, I'd like now to show you another video describing how the use of accelerated bridge construction saved us, the public, between $5 and $9 million on this project.
Nestled in the scenic Wasatch Front, the 4500 South Bridge over I-215 East is being replaced using an innovative process called Accelerated Bridge Construction, or ABC, which allows for the building of a new bridge in a staging area until it is moved into place. The existing bridge is old and is being replaced with a single-span bridge that is the same size as the current one. Vehicles will continue to use 4500 South and I-215 while the new bridge and abutments are being built. The abutments, as seen from 215, will contain artistic reliefs, helping the new structure to blend in with its picturesque surroundings. During excavation, soil nail walls are used to stabilize the west and east sides while traffic moves overhead. The staging area is located between the interstate and the southbound off-ramp to 4500 South in what is known as the Ramp Gore area. The lower portion is graded to match the elevation of the southbound I-215 roadway, and the higher portion matches the elevation of northbound I-215. Temporary abutments are erected to allow construction of the superstructure, which is the primary support for the new bridge. Steel plate girders are laid across the temporary abutments, and then a cast-in-place deck is placed on the girders, along with integral end diaphragms. The completed 5-lane bridge weighs 3 million pounds, is 172 feet long, and rests on a 12% slope. A self-leveling trailer with multiple axles and wheels called a self-propelled modular transporter, or SPMT, is used to remove the old spans and move in the new one. Freight containers fill the gap between the trailer and the bridge bottom. The SPMT is controlled by remote control as the operator walks along with the trailer. Once under the northbound deck, the operator backs the SPMT out and carries the span to a demolition area. The special demolition area is located just beyond the staging area, and all demolition work will be done after the new bridge is in place and traffic is flowing again. The SPMT operator follows the same procedure for the southbound span across I-215, removing the deck and carting it off to the demolition area. The next step is to remove the rest of the old bridge and the vents. During this conventional demolition, extra care is taken to avoid damage to the new abutments on both the west and east sides. The final step before bringing in the new span is to remove the existing columns that supported the old bridge. In the staging area, near where the new span sits, a temporary ramp is set up to allow the SPMT trailers on the high portion of the staging area to travel onto the northbound roadway. The SPMTs are moved into position under the new span, and the bridge is lifted off of the temporary abutments. Jacks tilt the bridge to a 4% tilt to compensate for the 4% grade of the I-215 roadway. This allows the bridge to be level as the SPMTs travel downhill toward the new abutments. The bridge span is backed out onto the interstate while the ramp is removed so that the SPMTs can pass, and then the bridge is moved into place and set down on the new abutments. I-215 under 4500 South will be closed and reopened to traffic after one weekend. Traditional methods would have resulted in traffic impacts for 9 months. 4500 South remains closed for approximately 10 days, while the abutments are backfilled and precast concrete bridge approach panels are put in place. An asphalt roadway, barrier, curb and gutter, and sidewalks are tied into the bridge. The next steps include a polymer overlay of the deck and lane striping. Once those tasks are complete, traffic is flowing freely again on 4500 South and I-215. The final step is to restore the site with landscaping. This accelerated bridge construction is expected to be complete by mid-November 2007. The benefits of accelerated bridge construction, ABC, include minimizes traffic disruptions, improves work zone safety, and reduces on-site construction time.
I hope you were impressed by that. This will be the very first time that accelerated bridge construction has been used in the state of Utah, and one of the very first times in all of the United States. I'm very pleased I'll have the opportunity to be there on site this weekend when this transpires. It will be a historical event, in my opinion. Here's a picture of the actual deck right now waiting to be moved from its current location to its final resting place, and another shot of it looking from the north. I acknowledge Daniel Shao, who I mentioned earlier, for sharing this picture and also the video that I just showed you. You might be interested to know what is the cost associated with the rental of those self-propelled modular transporters. The contracted rental price for this project, for these mobile units, is $880,000, less than 1 month of user delay costs that would otherwise be associated with this project. I think we should applaud UDOT for their innovation in this respect. Well, I have focused my presentation on just one aspect, one element of our national infrastructure. It is deteriorating. In 2005, the American Society of Civil Engineers produced a report card, which has received significant publicity. As you can see, bridges received a grade of C. A C is not a good grade, yet it is the second highest grade given to any element of our infrastructure, second only to solid waste. What is the average grade of our infrastructure? The GPA given by ASCE is a D. This corresponds to poor. The next lowest grade would be an F, failing, inadequate to meet the needs. Because of the widespread deterioration that we're facing, this has been called a serious national problem, a tremendous problem, even a problem of unprecedented magnitude. And ASCE estimates that $1.6 trillion is needed over a 5-year period to bring all elements of our nation's infrastructure to a good condition, or a B grade. I encourage each of you to visit the website that I've posted here, asce.org/report card, to learn more about the national issues associated with funding and legislation that will make a difference for good for our infrastructure. You can also learn at this site about state issues and how you can make a difference. Thank you very much for your attention at this House of Learning lecture.